Variable forces number 3, we're looking at straight line vertical motion with variable acceleration. So here we have forces that are not constants, and just a little definition here. If you ever hear rectilinear motion as a phrase used, it's basically 1D motion and straight line motion as well. So it's only needs one spatial dimension, so we can relax any vector approach here while we're looking at this. We do still acknowledge that these are vector quantities when we're looking at displacement, velocity, acceleration, force. They are vector quantities. We're going to look at vertical rectilinear motion in this video, and we're going to consider things such as drag and in particular air resistance, and we'll look at this idea of terminal velocity, which sometimes appears in questions. So the drag, or in particular air resistance, is proportional to some power of the velocity, so it's relative to the velocity. So sometimes we get expressions of this form appear in tasks that we're doing, kv to the power n. Now it could be linear, so kv to the power 1 or kv squared. Occasionally it can have higher order powers, so it's a model that suits a certain set of circumstances. Occasionally it can be fractional. So we're going to have a look at that, and they're our drag forces, and mostly it's termed in regards to air resistance, that being our number one. So we don't need to consider air resistance as negligible anymore. You might not have had that opportunity before. So we're going to look at upwards motion and downwards motion in this video. First of all, we're going to look at downwards motion, and we can see a couple of photos there, and you might not have ever been in that position, but you could probably appreciate what is happening there. So somebody jumping off a cliff into a body of water there, they're likely to remain accelerating for the entire fall, and whereas this one, skydiver, has a parachute. So the point of the parachute is to increase wind drag, so it hits what's called the terminal velocity sooner, and it's had less time to accelerate due to its weight, and whereas somebody free falling would have to fall for a very long time before they hit terminal velocity. Let's have a closer look at this. So downwards motion, we have a mass of m moving vertically downwards. So at the beginning of consideration, it's got a downwards velocity, and forces applied, you've got the weight, and of course it's acting vertically downwards in our model, and the force of air resistance. Now that opposes the direction of the motion, so it acts vertically upwards, and you can see that there. So the resistance force again, as I said before, is proportional to some power of the body's velocity, and if we model downwards as positive, now it's arbitrary which direction you choose positive. Okay, that's your choice in any given model, and I'm going to do my best in this video to show a couple of ways of setting that up. We have, using Newton's second law, ma equals mg minus kv. So in this one here, again, we've chosen to go downwards as the positive, okay, and hence mg will have a positive coefficient, and minus kv to the power n. So as the body falls, it reaches this so-called terminal velocity. Some people consider it a limiting velocity, which makes sense. Let's call that v sub t, and v sub t is the limit as t approaches infinity of v of t. So it's for some velocity depending on time, it's when when t tends towards very, very large values, I guess is one way of putting it, and it will have its ultimate effect there. Okay, so we use the concept of the limit to treat it in a rigorous fashion, and this terminal velocity is used for downwards motion. If we model, again, if we choose to model down as positive, we would have a total, because acceleration is 0, we have the ma part from previously, which we had just up here. The ma part, a is 0, the acceleration is 0, it's hit its terminal velocity, it's not accelerating. Okay, its limiting velocity means acceleration is 0, so ma will be 0, and mg take kv terminal velocity to the power n should equal 0. Okay, so that's how we know we've hit terminal velocity, when we have those mathematical facts apparent. Now, a different scenario is when we have upwards motion. So if it's projected upwards, we might need to find, for example, the greatest height something reaches. Again, this is straight line motion. If we choose to use positive as up this time, we would have the following scenario where we have the weight and the drag force opposing the motion, both heading in the opposite direction. Of course, if you chose to do this, positive downwards, they'd all be added together, okay? But the initial velocity would be negative quantity, as would height above the ground, i.e. displacement. So if this is something that's starting to move upwards, the forces applied to the body again are the weight and the air resistance, which air resistance still opposes the motion. If it's being projected upwards, the air resistance is going down. Okay, if something's going down, the air resistance will oppose that. Okay, so it's always against you. All right, so we have a different model based on this scenario. If we choose to model upwards as positive, we would have these two negative quantities there, or you could factorize them as such. Again, it depends on how you set it up. So, time for an example. An object of mass 4 kilos is projected vertically upwards against air resistance that is proportional to the square of the speed, and we do know an extra fact here, so let's seize upon that. That air resistance is 20 newtons when the speed is 10 meters per second. Find the greatest height. Now, that's a fairly common thing to have to find in such a scenario. So we've got vertically upwards type motion. All right, and the initial velocity is 20 meters per second. Now, this is a fairly long question, and I'm going to go through it quickly, so be prepared to pause the video and review sections as you need to. So here we have straight line rectilinear motion, and with this one I've chosen to model it positive in the downwards direction. Okay, so it was projected upwards. I'm modeling down as the positive, and just a little note there, it doesn't matter. Okay, your answer will be the same. Just be careful about what you're designating as positive and negative. Just get that right. So we have to find the greatest height. So I'm going to call that quantity height x. It's up to you what you call it, and just writing down the given information there. And if you decode what's written in the text, it's a kV squared resistance force. Alright, so the initial velocity and that velocity at v equals, that information about when the velocity is v equals 10 allows us to find the k value, which is 0.2 or 1/5 there. That assists our further progress through the question. So consider known acceleration expressions. This is variable acceleration, so we know we can't use those constant acceleration bits of calculus, or if you're allowed to, the Suvat formulas. All right, so then they're no go for this. And we look at what's expressions might be helpful. We've got v and x are what we've been given to work with, and well, we need to find x, and that's important information, and v is given. So think about what we're given, and one of these two perhaps would be helpful. I've just made a little note to the side there that you might want to zoom in on. If you chose to use up as a positive direction, your initial expressions would be as such there with the negatives. Okay, all right, so downwards is positive. Let's proceed. So we've got Newton's law looking at total forces. So ma equals mg plus kv squared. Always draw a little diagram, or at least put in the key vectors, and we substitute our values in and dividing through by 4. Okay, and then we sub in one of those suitable values. This one is v dv dx. Okay, and then we go ahead. I've just got some notes there about once we get to the point where we're doing the integration, separation of variable style, we've got a few things to consider if you're having trouble applying this, which if you're watching this video you should be familiar with, pause and take note here about that constant to keep the overall values the same. Okay, so doing the integration to both sides, putting the constant on the right hand side, dividing through by 10, putting in an exponential form, which gives us this expression which I've called statement 1. Now we have an arbitrary constant there which we need to get rid of, so we apply the initial conditions. Notice I'm just leaving g as g instead of writing an approximation of say 9.8. Subbing in those initial conditions and taking logs of both sides down to here. Okay, and then we get another expression for c, which I've called statement number 2. Now going back to statement 1 and subbing in that information from statement 2, we get this line here. Alright, and we are basically applying various exponential and log laws and factorizing, rearranging. We can see what we get next. We've got a fairly complex looking expression for v squared, and what I've chosen to do is actually put it in terms of v, and we get two solutions there considering only upwards motion. So in other words, we're going to use the negative solution because we've considered down as positive. Okay, so we're actually going to choose the negative in this case. So using an important fact, now hopefully you realize velocity will be 0 when it reaches its greatest height. Okay, so we set the velocity equal to 0 there, and we go through and algebraically rearrange, and we get an expression which involves x, but it's in terms of g, so we need to rearrange and we need to take logs to both sides, multiply through by 10, and we get an answer which is negative, and that's fine. It's 11.12 negative. Now that's fine because that means above the ground, because we've considered down as positive. Okay, and if you did the opposite you get a positive answer.